All right. So for this part, we're going to do the register allocation exercise 8.1. And for this one, we're given an example program that we're going to go through. You can find this one in the textbook. So yeah, let's go through it. We'll start off with question A, which says show the suck gen kill for every instruction in the program. And this one should be very simple to do. Remember that the suc set is the set of instructions that come after, at least that would come after the current instruction I. And we'll start off over here. So what instruction would come after instruction 1? It would be instruction 2. And yeah, I think that's it. And which instruction would come after instruction 2? So for this one, since it's an if statement, meaning that if A less than B, then next. So it could either jump to instruction 7 and go over here, or go to swap, which is instruction 3 over here. So that means the next instructions for this could be 3 or 7. And if we're in instruction 3, the next instruction will be 4. Here it's going to be 5, and here it's going to be 6, here it's going to be 7, here it's going to be 8. 9, b mod 9, so this is just going to be 10. And then we have another if statement, so this is going to be if b equals to z, then and, where's the and? So it's going to be 11. So it's either 11, else start. Where's the start? Start is instruction 1. So it goes all the way back to instruction 1. I just wish when I press enter, it takes me to the next one. But um, for instruction 11, we go to 12, and for instruction 12, since it's a return, it's just going to be an empty set. So yeah, that's the first bit. And then gen, this is the set of all. It is the set of all variables that instruction I generates liveness for. So if we are using a value of a variable, or if we're using a variable, that variable would be included in this set. So we have instruction 1, which is label start. There is no variable here. Start is not a variable. It's just a label. So it doesn't store any memory or such. So we can leave that. So we're here, if a less than b. So we're using the variables a and variables b. Then next, then else swap. So these are labels, so they're not actual variables. So we're just going to skip those. So the answer here will be a and b. Label swap, not a variable. So it's just gonna, so we're not using any variables here. And here, we are using the variable of a and we're assigning it to t. So we're not using t because we're giving it a new variable. So we're not generating liveness for it. So this is just going to be a. Again, I keep forgetting. Then here, same idea. We're using the variable b, but not a because a is being assigned with a new variable. And then over here, it's just going to be t, not b. Uh, I did not check, just to be, I do not, I'd have to remember if I did check if they mentioned if any of these are constants, but I doubt that. I doubt that. So label next, no variables here. I think that's the number 0 and to z, so nothing here. We're not using the variable z. We're assigning a new value, so we're not using it. Then we're using b, b mod, and ba. So we're using the variable b when, but we're also assigning it. But because we're using it, it's live, still live. So we're just gonna say b here, and we're also using a. Okay, I keep messing that up. Okay, if b equals to z, bad programming here, then end else start. So we're using b and z. Then no variable here, and here, since we're saying return a, we're using the value of a, so we're just going to say a. And that is the gen set. I think we did it correctly. And now we're going to move on to the kill set, and the kill set is the set of all variables that is the liveness. We're going to assign them a new value. So we're going to have label start, not a variable, so we're not using that. Nothing is being assigned a new value here, so we move on. Nothing, the instruction 3 has no new values. But over here, let me zoom in case it's not too clear. We're assigning t a new value, so that means we're gonna put t in here because we're assigning it a new value, and a as well, and b. So since we're assigning them new values, they're gonna be part of the kill set, and z as well, and b as well. And then if b equals to z and whatnot, so this is just a conditional statement and not an assignment, so nothing's happening here, nothing here, nothing there. And that is our Succ gen kill set. But then section A, we're going to do section B, or question B, where it says calculate in and out for every instruction in the program. Show the iteration as in figure 8.4. And figure 8.4 in the textbook refers to a table that looks exactly like this one, where the first few columns are the initial um, any steps or the initial phase of the fixed point iteration. And the way it works is that we'll start off with an empty set for all the values of out of I and in of I. And then with each iteration, we're going to populate it with values as we go. And to help us with these calculations, we're going to make use of this formula. And I also have this little text box here just for me. So the way we're going to do for each iteration, we're going to start off with the last instruction. So we're going to calculate the out of the last instruction, followed by the in of the last instruction, and then the second out of the second last instruction, and the second last, and then the in of the second last instruction, all the way until the first one, where we have in of 1, and obviously, and the out of 1 as well. And the reason we do it in this order is so that it becomes it's way easier to get your values faster compared to doing it like from the top down or in any other order. And we'll start off with this column and then that column and then so on. So what I'm going to do first is that what I like to do personally is you can do your calculations over here, but I like doing it on the side, like so. And once I get the values over here, I'm going to do it. So, okay, so I like to do all the values until we reach the end. Yeah, until we reach the end. And once I have the values, then I'll populate each and every column, and that will signal the end of the iteration, and then we'll just do it again. You can populate the values over here, but I just prefer to do it this way. So I'm gonna do the first few with you guys, and then I'll just fast forward to the end. Maybe I'll play some copyrighted music. Who knows? So start off with this. So this is going to equal to in. So since what's his suck of I? In this case, suck of I is an empty set over here. So we're gonna do suck of number 12. So I is 12 at the moment, and it's an empty set. And since we're going to say J of an empty set, this will evaluate to no value at all. So this is just going to be an empty set. And then we're gonna do n of 12. So n of 12 will be the gen of I and the out of I. Let me just move this to the top so that it's easier. I don't have to give any of you guys motion sickness from scrolling up and down. So we're gonna have and move this up. So we're going to have oopsie. Okay, n of 12, it's going to equal to gen of 12 union out of 12. And just extend this a bit more out of 12. And we're going to apply the set difference. The set difference, I'll explain it in a bit. So we're gonna take the set of this, and we're going to remove all the elements found in this. So we're just scratching them off. And so that's how the set difference works. So the gen of 12 is the values A, the set of A, union, what's this? It's an empty set. Since it's an empty set, we know that the final answer will be empty, and the kill of 12 is also empty. So our final value here is this. And now we're gonna do out of 11 equals to what? Out of 11, what is the suc of I? Suc of I is suc of I in this case is now 11, and suc of 11 is just 12. That means we're gonna have this 12, just 12, and there's nothing else in the set, so it's just going to be this. And what is the n of 12? We don't have the the n of 12 is just going to be A. Just going to be A. There you go. And now we're gonna do n of 11. N of 11 will equal n of 11 will equal to gen of 11 union out of 11. Okay, out of 11 set difference kill of 11. And what do we have here? So gen of 11 is an empty set because yeah, it makes sense. It's the instruction is a label, so there's no variables. And the out of 11 is just gonna be A. And the kill of 11 is just this. So our final answer will just be uh, empty set union A, and which is just going to evaluate to just A. And yeah, this just goes on for a while, so I'll just keep quiet. You can watch along or do it alongside me, see if we both get the same answer. Yeah, if I have any music to play, I'll play it. Um, do 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 do. So let's look at Gen of 12. What's Gen of 10? Oh, okay. Guess I'll keep it going. I'll keep talking. Well, mm, I don't have the most soothing voice, so okay. What's this? So we're gonna have what's the sec? So since the sec is two valid, it's gonna be sec of 11 union in of what? And then we don't have so in of 11. We know that it's going to be A, and the in of 1 we don't. At the moment when we look, it's currently empty. So this is just going to be empty. So the final answer we have here is just going to be A. Okay, there we are finally done. Oh my lordy lord. That took a minute. So yeah, this is the final evaluation. I'm just gonna plop everything in. Um, yeah, let's see. Hopefully this is much faster. Okay, so here's the first iteration that I got. Hopefully it's right. I tried to be as diligent as possible. Here's my working for iteration one. Just move this a bit up. So it does take a while to do this, especially like I'm not sure if it me doing it on a computer, if I'll be faster on paper, but this is how it looks like. You can pause to see, you can compare it. If I made a mistake, it's probably somewhere in here, but I think it's all right. So yeah, so that's the first iteration. You just do the same for the second iteration and for the third iteration until it's correct. So that is what I'm gonna do now. And yeah. So that means I'm gonna have to make a copy of this, a duplicate, and then name this iteration two. And then we're gonna keep doing this. How many iterations? Okay, we're done with iteration three. I don't think there's been any changes. So yeah, after iteration two, everything just stays the same. I'm still gonna fill it in just to double check. Oh yeah, hopefully you enjoyed the music. Yeah, I had I was listening to nothing. I was just staring at the screen. You I mean, it sounds sad, but that's because it is. But it's life. It's good to give yourself time to think. I don't have much to think about really. Everything is going all right. Yeah. All right. And like that, we are done with B. It took a while. Generating this table by hand is hell, I won't lie. So that's how you do it. Uh, yeah, I don't have any comments here, really. I'm being honest. I don't have any comments. You know what the process is. You start from iteration one, you build up as many values as you can, as many as you can in the first iteration, and then you do it again with the new values, updating the old sets to have the new values. And that is how you answer uh, B. And that is how you get the in and out sets as well. So now that you have the in and out sets, what can you do? You can do the next question, I suppose. Question C. And to do question C, it's all we just completed the section B over here where we got the outset and the inset. And now that we've done this, liveness analysis is complete. Our next question is asking us to make an interference graph and to define the interference between uh, elements, we make use of this definition here, where a variable x interferes with variable y if x is not y, and there is an instruction I such that x is an element of X is an element of the kill set I, the kill set of instruction I, and Y is an element of the outset of instruction I, and instruction I is not X equals to Y over here. So based on this, we can all we'd have to do is look at this over here. I wish I also so I just got the iteration 3 outset and the kill set as well. Looks like I'm missing the instructions themselves. And then put it next to over here so that we can make use of it. All right, so we just have to find out what interferes with what based on this. So what matters, we're gonna look at the ones with the kill set because it's like the first thing, and then we're gonna also look at the y is an element of the outset. So also just this is why we have this. And instruction I is not x equals to y. So when we're assigning, we're not assigning y to x because that does not count as an interference. Now when we look at that, what do we get? So we have t, b, and t. The instruction 4. So instruction 4 is t equals to a. So we don't see a here. So t interferes with b over here. There is a nicer way of doing this. I don't have the table anymore, but we're just going to just make connections. So b, so b t equal interferes with b. So we're gonna take this and connect it. It's a bidirectional relationship. And t cannot interfere with itself because x is not equal to t. So that's the first one got. Now what else? Then we have A, so instruction A, so this is going to be instruction 5, A equals to B. And then here we're going to have A and T. So A cannot interfere with A, but A can interfere with T. So we're just going to have this as well. And that's it. Then what else do we have? Then we're going to have B. So B, the instruction is B equals to T, and we don't see T here, so we don't have to worry about that. B interferes with A, which is valid, so we're gonna create that connection, but B cannot interfere with B. And then we're gonna skip this, we're gonna do Z. Z equals, here the instruction is Z equals to 0, so we don't have to worry about this condition over here. So Z interferes with A. Let's make that connection. Z interferes with A, and then Z interferes with B. And I'm just gonna put this over here. Interferes with B, and that works. And then B interferes with, so B equals to B mod A. So yeah. So it's not the same as this over here, so it doesn't matter too much. So B interferes with A, we already have that, and then B interferes with B. That's not allowed because B cannot equal B. Then B interferes with Z over here. And yeah, I think that is it. A better way to have done this was to make use of the was to make a interfere table, which is similar to, oops, I'm just making a quick copy on my right hand side. So a better way would have been to just make this table over here and just make the connections, but this works too. This works too. Now we have our interference graph over here. Uh, I'll just put this there. Okay. Just stop. Now we're going to move on to make a 3 coloring interference graph show the stack as in 8.6. So this is the stack as in 8.6, and this is how it's supposed to be made. We just grab this graph that we made over here, and we make use of the algorithm that was given to us. Let's see. So the algorithm that we're supposed to use. Um, okay, I think yeah, there you are. Found it. I'm just copying it onto my side. It should have been quicker with this. So yeah, okay, here it is. So the algorithm from the textbook that we are supposed to use is this. And in our case, since we're told that it's a three coloring of the interference, that means we're gonna have three colors, meaning that n is three. I'm trying to move this graph over here, which means that n is three. So I'm just gonna make note of that here. So n is three. And so we're gonna start with an empty stack. So it's currently empty. Find any node with fewer than three edges. So n is 3, and find any node with fewer than three edges, where n is the number of available registers. Yeah, there are available colors as well. So anyone with less than 3. So this one has less than 3, and this one has less than 3. So we can pick any of the two. Let's pick T. Okay, so we're gonna say node T and its neighbors. So we're going to write down it along with the neighbors that it's connected to. So B and A. So we're going to keep doing these two instructions until we run out. So I think I'll just delete this so that it's much easier. So find any node with fewer than three edges, where n is the number of available registers of colors. So any of these qualify. So we're going to go with Z. We're gonna Z, then we're just gonna be like B and A. Now we're gonna delete that. And same thing, we're gonna say B, where the only name is A. Then we remove this, and then A is just gonna be A. It has no neighbors. I think we can just pop it out. And let's see. Now that we've like done that, I'm just gonna make another copy. So now the way this out, now the next step of this algorithm is okay, if no node has okay, if we're done with this phase, we're gonna move on to this phase over here. And then pop a node and its list items from the stack and assign it a color that is different from its connected nodes. If this is not possible, coloring fails, that node we mark it as spilled. So we're gonna assign it a color that its children doesn't have. So since this is the top of the stack, we're gonna assign it. So let's pick our colors for the ones that we're gonna work with. I think that so we're gonna have this color over here, and then this color over here, and then okay, that's a very bad choice of color. I'm just gonna use another one, a blue. Okay. So we're gonna assign it the color blue because none of that. Actually, no, we can even just use a number. Just say color 1. Uh, so yeah, I think, and then I'll just write 1, 2, 3 so that I don't forget. So we're gonna have the color 1, and then B. What B do we assign node? The node. What color do we assign to node B? Since 1 is already taken, we're gonna just say 2. 1. Now we have to assign Z a color. So Z, can we give it 1? We cannot because 1 is already taken by A. And again, we cannot assign a color that neighbors have. Then we have B over here. So B, can we assign Z number 2 or the color 2? No, we cannot because B already has that color. So we're going to assign it the color 3. And for T, what color can we assign it? Can we assign it 1? No, we cannot. What about 2? No, we cannot. What about 3? Yes, we can. And here we are. So in here we have no spillage. So B, so A has the color 1, which is this one over here. That's a marker, I think. Isn't that supposed to do the background? Okay, yeah, this one. Here we are. And then 2, here we are. And then 3. There you go. And there you go. So here, there's no spillage of any sort, so we don't have to change anything. Oh yeah, that's how we do D. And now it says attempt to do the same thing, but select variables for spill. Do the spill transformation as shown in section 8.5. I'll have to check that section again and redo the complete register allocation process on the transform program. If necessary, repeat the process until register is successful. I am not doing that again. I am not doing the liveness analysis again. Just putting it out there. But if we were to do the exact same thing, so let's assume that we did. So we're gonna do the exact same thing, but this time with n equals to 2. So that means we'll still apply the same technique. We're just gonna copy this table over here. Copy. Okay, I see. So we're just gonna copy this table. Then we're gonna copy this over here. So if n equals to 2, we just apply the same thing. Let's say we do the exact same process again. So we have A, we assign it 1, 2, we assign it 1. Then we come over here. Since this is 3, we're gonna mark it as spilled because we've run out of colors. And this one we're gonna mark it as spilled again. And so now that these are marked as spilled, only these two will have colors. So I think this we marked it as green, and this one we marked it as red. So if you're wondering how we got here, just do the exact same thing we did here, but with only 2 colors. And you'll end up with that these two don't have any colors, and we just mark them as spilled. So for that, we can just say spilled, or just the kind of thing. Copy this, type in spilled. That means we're going to have to allocate them into main memory. So we're going to do this, and then we're going to do that. And the way this works, okay, so now that we've spilled these 2 variables, what do we do next? The next step is to generate new code for where these 2 variables are in main memory instead of registers. So we won't be able to allocate registers. These 2 we can allocate the registers, so we can keep them as they are, but these 2 we'd have to rewrite the code such that they stay in main memory. At least they're stored in main memory rather than registers. And we're gonna look at section 5.5, but I'm pretty sure it tells us how to rearrange the at least how to replace Z and T to make use of main memory. And it's very simple. And we are back. So this is the section from 5.8.5, which talks about spilling, and these are the instructions you have to follow in order to, if a variable has been marked as spilled, this is how we replace them in the code. So this when we have chosen one or more variables for spilling, we change the program so these are kept in memory. To be precise, for each spilled variable, we first choose memory address x where the value of x is stored. So the memory address that we're going to store our spilled variables. So this is we're just gonna say first let me just stop this. So we're just going to say I just need to copy this. So this is where we're going to store the memory address that we're going to store T, and the memory address that we're going to store Z. Yeah, so these are the memory addresses. So we have to insert these. So we're gonna replace where we're using T with Z and such. Let's see. In every instruction that reads or assigns X, we locally in this instruction rename X to XI. So everywhere we're reading or using that value or assigning it. So we have T over here. So let's see. This is good. This is good. So we have T. So we're gonna rename this to T4. Um, this is good. This is good. This is gonna be T6, and this is gonna be Z8. This is going to be Z10, and I think that's everything. I think that's all of them. So yeah, that's the first so that's the first one down. That's the first one down. So we've done this, we've done that, and now let's see. Before each instruction that reads xi, insert instruction xi equals to memory address xset. So everywhere before we read, so that would be let's see, it would be this spot. Let me see carefully. If AX is less than this, so it would be this. How do I insert above? It's okay. So I'm just gonna rename this to 4, and then T4 equals to A. So that means before we answer, so we don't have to change the number line here. Everywhere before we read, we're gonna say T4 equals to memory address T. And then let's keep this going. So same idea over here. Actually, I can just add it over here. Boom, there we go. Um, let's see. T6 equals to memory address T. There you go. And over here as well, insert at the bottom. We're gonna say Z8 equals to memory address Z. And over here, we're gonna insert. This is going to be Z10 equals to memory address Z. And I think that's everything. And let's see. Oh, this is where we read it, right? Yeah. Right? Did I mess up? Before, let's see. Oh, yeah, I made a whoopsie over here. I made a whoopsie over here, but let's see. After instruction I insert. Yeah, I made a mistake. I'll just fix that. I was a bit too eager, but I did insert. So these are correct for when we're reading. Okay, not. Let me just start all over. Let's start all over. Okay. So what we're gonna do this choose memory address X where to store the value of X. So we're gonna choose the memory addresses where we're gonna store our spilled variables, which would be T and Z. So we're going to store value T into memory address underscore T or address T for sure. And here we're gonna store what's our other spilled value? I think it's Z. So we're gonna store it over there. So now that's step one complete. In every instruction that reads or assigns X, we locally rename the instruction from X to XI. So everywhere we read or assign. So we assigning over here T, so we're gonna name it to T4. Here on instruction 6, we are using it. We're gonna rename it to T6. We're using Z over here, so we're gonna rename it to Z8. That's good. So here we're using 10, so we're gonna rename it to Z10. Looks good to me. And let's see. So I think we're done with this instruction over here. Before an instruction I that reads IX, insert instruction in IX equals to memory address underscore X. So before we reading, so everywhere we're using and not assigning. So we're using it over here. We're using T6 here, and we're using Z10 over there. So let's go through it. So over here, we're gonna right before. Okay. So right before, how do I? Okay, now let's just add them. I'm just trying to add. There you go. Okay, there you go. Yeah, right before. So we're just gonna say T6. T6 equals to memory address T. And here we're using and not assigning, so that's good. So okay, over here. So we're just gonna add underneath. So here it's going to be Z10 would be equals to memory address Z. And let's see. I think we're done. Okay, I think we're done. If I missed anything, okay, T6. Yeah, we're good here. We're good. So that's where we are reading and not assigning. So we're done here. So after an instruction I that assigns xi, insert instruction m is here. So to this, so we're gonna after each assignment, so like over here and over here, and I don't think anywhere else. So after we assign, so after here, we just give it a new value. So we're just going to add memory address t equals to memory address t4. We're assigning over here as well, so we're gonna add a new line. So memory address z equals to C8. And I think that is everywhere. I think we're good. Yeah, I think that's it. That's the new instruction. And from here, you just do liveness analysis again. But let me read. If x is an input parameter, hmm, input parameter, I'm guessing like if they say input parameter, I'm assuming the function input over here. D, so this is an input parameter for the function. If x is an input parameter, add instruction address underscore x, this to the start of the function. Note that we use the original name. So yeah, we don't have to do this, neither z or t or z like that. So that would be, so the final code, at least not the final code, you'd have to do liveness analysis. And what I mean by liveness analysis, you'd have to calculate the succ, the gen, and the kill, and then the in, and then the out. And then you'd have to draw the graph all over again and redo that whole process and see if there's a spill or not. And yeah, I don't feel like doing that, but now you know how to do it, and hopefully chapter 8 is a good. Do read the rest of the book to get a better understanding, but that's how the chapter is structured and how it works. But yeah, thank you for sticking with me for this long. Good luck. If you have any questions, do post in the comment section, and hopefully you guys will help each other out. Will I reach out? I don't know.